All right, so we got this rancher that has 400 feet of fencing and wants to enclose two adjacent rectangular corrals shown in this figure. And he wants to figure out what dimensions to make the fencing on the sides and wants, basically to get the most area. Like what should he make this side and this side so he gets the biggest area when he's only going to be restricted to 400 feet of fencing. So let's draw like first like a more clear diagram up here to really show what's going on here. So it's basically broken down to two pens. So these side lengths we're going to have represented by y. So we got y, y, y. And we got x from here to here, here to here, here to here, and here to here. So the fencing's all the way around the perimeter plus this segment length here. So then all that fencing has to add up to 400. And then so 400 will be 3y plus 4x. Now, the area of the entire rectangle, this whole thing will be, y to the side length times the other side length, y times 2x. It's all the way across is 2x. So we can just write, let me just write 2yx. So we want to optimize. We want to get the most area. So this is going to be our primary equation that we're going to have to work with. So we're going to have to figure this out. So the idea is to find an equation for area in terms of just one variable. Let's just say x to keep it simple. Well, not simple, just because x is usually common. So let's make an equation for area in terms of just x. Then we can find the maximum area by differentiating the area with respect to x, finding the critical values, and then seeing how those critical values behave relative to each other. We could do the first derivative test, second derivative test, or just compare function values. It just depends on the problem. But let's first start solving for y in terms of x so that we can write this in terms of just x. So we're going to use this equation. We solve for y. So we're going to have 3y equals 400 minus 4x. Divide everything by 3. And so we get y equals 400 over 3 minus 4/3 x. So then with this, we can make a new equation for area. We'll just have it be a, where area will be 2 times 400 over 3 minus 4/3 x. All this times x. Rewriting it, we'll get area is multiplying everything by x and the 2, we'll get 800 x minus 8/3 x squared. Now, we got an equation for area in terms of just x. So let's find the derivative of area with respect to x and find the critical values and figure out what's going on at those critical values. Those critical values will give you a maximum. So let's go and find the derivative of area with respect to x. So simply just be 800 minus 16/3 x. To find the critical values, we're going to set the derivative equal to 0 and solve for the zeros. So 0 will be equal to this. Solving for x, adding 16/3 x, dividing by 16, we'll get x is 50. So here's one critical value. We don't have any undefined values because we can plug in any equation for x into this equation and we'll be okay. So this is our only critical value that we have to inspect. Now, this is the thing. Like how you go about checking this critical value is really up to you. And I really advise you to take your time and think about this part rather than just rushing through like, oh, first derivative test, second derivative test, whatever. Because some problems are we're gonna be more complicated by doing one method versus the other, and some you can make really simple, and some you actually don't even need calculus if you just recognize the math that's going on. And I'm actually going to show you what I mean in this problem because we actually didn't even need a calculus in this problem because we have a quadratic here and we have a linear function. So let's first, I'll get to that in just a second, but let me first talk about restrictions on the domain because you know if we're dealing with a real life scenario, there's only going to be a certain number of values that y and x could be. Y can't obviously be negative. X can't obviously be negative because we're talking about, the feet of fencing. So let's over here, let's rewrite and let's show that with the x, with the domain and range for x and y could be. So x could go from, it can't technically be zero because you wouldn't have any width, but it could be anything bigger than zero, hypothetically speaking. So we're going to make it, anything bigger than zero. And then the biggest value x could be to make this equation work would just be basically up to 100. It wouldn't be able to be 100 because if you make x 100, then y is 0. But it could be anything more. It can be anything up to 100, hypothetically speaking. So x can go from 0 to 100. This is all x can go from. You can't have any values less than 0 or any values beyond 100. Now, y obviously will not be able to be 0 or less either. But then if we want to find the maximum value for y, if we were to say again, if we could make x technically, if we could technically make x 0, y would then be up to 400 over 3 feet, 400 thirds, or like 133.33 repeating feet. So the largest maximum value would be right up to 400 thirds. So we're going to basically have an open domain and range. So these are all the values that we're restricted to for x and y. What's my point here? The point is that there's one way you can do this is just using what we learned at the very beginning of the chapter. We can just compare the value of the area when x is 0, when x is 50, and when x is 100. Because that's basically going to be where all your potential maximum and minimum values could occur. And you could just figure out which one's the biggest because we have an equation for area right here. Now, the other way is you can find the first derivative and see how it's behaving on open intervals, or you can find the second derivative and see the concavity. Again, I'm taking my time to explain all this. I feel like this is important and something I want to always emphasize in my students because it's important you understand what's going on here. So, for example, if I just did the very simple way we learned in the first section of this chapter, I would just I would basically find the area when x is 0. When area of x is 0, it wouldn't work. So like a of 0, let's say, a of 0 would give me an area of 0. That wouldn't work. Then I compare it to a of 50. I would plug 50 into there and there, and I would get like something like I think 6,000. Yeah, basically it's 6,600 repeating, 6,666. I don't like this number repeating. And then if I compare it to the area when x is 100 or up to 100, again, technically we couldn't make it to 100, we can make it up to 100. We would then again get, we would get 0 again. So the maximum occurs here. This will be the maximum. The maximum area. The maximum area occurs when x is 50 and y equals, we solve for y, we can find the y value in, in any equation that we're given for y or x or anything. We can find it here. But will basically occur when y is 200 thirds feet. Both these are feet. Now I'm going to keep on talking and explain more about this problem because I think it's key. But here's your solution if you want it and just want to move on. Now, what I mean by this is, okay, so like this, this tells you the equation of the area. And if you remember from just algebra 2 days, this is just a parabola. You can just technically graph this and find the vertex of the parabola. This parabola tells you the area. If I was just to graph this, I could find the vertex, using negative x equals negative b over 2a and plugging in, finding the y value. I'm not going to show that work, but the point is that you're going to get this parabola that has a maximum or a vertex at 50 commas this 50 comma this value, 50 comma 6,666.6 ish. This is the area function. This is this equation right here. So it's going to have intercepts at 0 at the origin, and it's going to have intercepts at 100, 0. And I have a more precise graph. I put it on here, and you can see this is the graph of the quadratic. So again, you don't actually need calculus for this problem if you just think about it and realize this is a quadratic equation. And then obviously the maximum area is going to occur at the top when x is 50. So you can actually find your answer like that. Now, the other thing you could do is if you want to look at the first derivative and analyze it, in a calculus way, the first derivative is this equation. This equation, think for a second what that equation would be, even though it looks more complicated than it is. This is just the equation of a line. This is just the equation of a line with a slope of negative 16 thirds and a y-intercept of 800 over 3, 800 thirds. So the line basically does this thing. It will intersect the x-axis at 50 because that's when the derivative is 0. Because remember, this is the equation of the derivative. This is the equation of dA dx. So if you were thinking about this using the first derivative test, what's going on here is the first derivative is positive here. The first derivative is negative here. So this means this is telling you that the function is increasing here. This is where it's increasing. Going from this graph to this graph, this tells you that it's going up, up, up. Like right here, see, it's increasing. That's what this is showing. At this point, the derivative is negative, and that is showing that the parabola is decreasing. That's why the maximum occurs at 50. You can go connect both and both. So the point being is make sure you understand this part when you're doing these problems, because sometimes you're going to get an answer in one way, you may not get it because it's just not the way you will naturally think. But if you do it another way, it makes a lot more sense. Keep that in mind because I could even go another step further and show you the second derivative. That second derivative will be negative everywhere. I'll just show you actually right now. It's just because I can. If I want to find the second derivative area with respect to x, I'm taking the derivative here. It's negative 16 thirds. What does that tell you? You're like, well, how do you know? How do you do second derivative test? You don't have to do a test. The second derivative is always negative. This tells you the graph of the function is always concave down. It tells you that the derivative is always decreasing. So again, this is another way to just tell you, okay, well, that means the maximum will occur at that point we just found, 50. Well, technically, this wouldn't be the maximum of the second derivative. This just tells you that the graph, the function is concave down. So again, that's another way. So keep that in mind when you're working through these problems.